Let's wait for 2 3 minutes. After that, I will start. Okay, we can start. So this is 10th week. So this is the 10th week problem solving session, the advanced atmospheric physics. Uh, so as we have done earlier also, that first today's plan will be to discuss the assignment 9 questions, which has two, I think, numericals. So we will solve those. And once we have done that, then we will go towards the week 10 content that will be helpful for solving the assignment questions of week 10. So this will be the plan for today. Okay. So at the beginning, so we will be going through the assignment question. Okay. So let me open the assignment here. Yeah. Okay. So the assignment 9, the first question, it asks that which of the following ionic species could have smallest recombination rate near 150 kilometers? So we know that based on our previous problem solving session and week 9 contents, if you just go through, you will find out that at 150 kilometers, the major concentration of O plus, that is oxygen ion, this O plus ion is of large quantity, and the recombination rate is much smaller for in case of O plus as compared to any other ionic species. So we have seen that there are dissociative reactions, right? Radiative recombination, dissociative recombination, where we have found that the radiative recombination process, which includes this O positive ion, is having the smallest recombination rate, right? Which is about, it takes large amount of time. So about 10 to the power 6 seconds. So which is very large. So the smallest recombination rate. So if I have to write here, then for the first question, you can write that at, first of all, at 150 kilometers, concentration of O positive is large because we can see that in that those layers, the O positive concentration is maximum. And so this is the first. Number two is that, uh, just remember the concepts of radiative recombination process, which includes this O positive ion recombination. So radiative recombination process of O positive. So O plus plus this electron. This is the recombination. So it is combining the electron again and becoming O plus H nu, sending some photon. So this process have or has the smallest recombination rate. And time it takes, time taken for these processes is approximately 10 to the power 6, which is a very large time. Okay. Because of the small recombination rate, the time taken is very strong or large. Okay. So now the second one, let's go to the second question. So the first question is O positive is the accepted answer. Second is that which species has the highest temperature in the F2 region of the atmosphere? So just if you remember, there is a plot where the temperatures are being plotted with altitudes, right? So in the previous uh, section only, so suppose this is your Z, this is the altitude, and this is the temperature at Kelvin. So you find that at upper atmosphere, this is the neutral temperature, and if you go further like this becomes the temperature of the ions. And further, if you go, you see that the temperature of the electrons is much, much stronger. So electrons, right? So electrons in here F2 layer is being mentioned. So electrons in F2 layer has highest temperature. Right. So this is the second question. Okay, let's go to the third one. So if a planet having the same mass and radius as of the Earth and has an atmosphere which is made up of 78% of nitrogen, 22% of oxygen molecules. It also has isothermal temperature of 300 Kelvin. Then what should be the scale height of its atmosphere? Simple. So this question is particularly focused on calculating the scale height of the atmosphere, and it is the Earth-like planet. So it is mentioned here, mass and radius are the same, and atmosphere constitutes of 78% nitrogen, 22% oxygen. Although in case of Earth's atmosphere, it is not exactly 22% of oxygen, it is 21 point something, and others are the different other trace gases as well as which constitutes of the greenhouse gases and all others. Right. So we will just focus on nitrogen and oxygen. So how will we calculate what is the expression of the scale height? And very important, uh, in the question it is mentioned, the isothermal temperature. So this scale height is majorly defined for an isothermal atmosphere. So Earth, right, planet, planet with isothermal atmosphere. Very important term. Only then we can calculate the scale heights the way which we have defined in the previous session. Okay, so isothermal atmosphere. This is very important. Isothermal atmosphere is very important. And what is the temperature given? Isothermal, the temperature is given to be 300 Kelvin. That is, throughout the atmosphere, we have the temperature as the 300 Kelvin. Now, given are the atmospheric composition, right? It does not consisting of only one atomic species or one molecular species. So here, percentage contribution, composition of the atmosphere is given. That is, it consists of nitrogen and oxygen. All other gases are, they have assumed that they are trace, they are not as much as compared to the N2 and O2. So N2 they have said that consists of 78% of the atmosphere, and here by volume, here 22%. Right? Now, for the scale height, so what is the expression of the scale height? That let us learn. So, what is the expression of the scale height? So, suppose h is the scale height. So, h can be written as, there are many different expressions, but what we will write is that what generally I have told that I prefer is R star T divided by N into G, where N is the, if you have many multiple species, just like here, you have to say the mean molecular mass. Molecular mass is not the right term. I would say mean molar mass. Because if you remember, when we have derived these expressions of scale height based on, or writing it in terms of R, that is universal gas constant, in this case, we have used the M as the molar mass of the ionic species or any atom or combination of many molecules. Okay, so we will be using a mean molar mass. So how to calculate the mean molar mass? So how to calculate? So let us write it here. M bar. So M bar is the mean molar mass. So how to calculate that? So you have been given this N2 and O2 composition. Based on that, we will calculate. So we know. Let us write that. We know that the molar mass of nitrogen is 28 grams per mole. Okay. Approximately. There will be decimal places and all those things. I am neglecting all these things. And the molar mass of oxygen is about 32 grams per mole because oxygen atom is 60. So 16 into 2, 32, and this is N is 14, so 14 into 2, 20. Perfect. Now we have to calculate M bar based on the composition given. Simple. It is the percentage composition of nitrogen times the molar mass of nitrogen. So let us write this plus the percentage, right? Yeah, the percentage composition of oxygen into the molar mass of oxygen. This is how you can calculate. And finally, because it's a weighted molar mass, so you have to just put the composition here. Okay. You can write it in. any term, so that is fine. Okay. 17% instead of going into the percent, let's go ahead with 0.7. This is how also we can write, right? Because the nitrogen is given to be 17%. So 17 per 100. So 0.7. Okay. So this into 28 plus. What about oxygen? 0.22 because 22% into 32. And if you write in the denominator, it's 0.78 plus 0.22, which will give you 1. So finally, you are just going to calculate the numerator 28 plus 0.22 into 32 divided by. So you get this next one. So this molar mass will come out to be roughly about 28.88 or 89 something will come grams per mole. Remember, these are molar mass. So it will be in grams per mole. Okay. So 28.89 grams per mole is the mean molar mass when you have the atmosphere having composition nitrogen and oxygen only with this amount of percentage. Okay. Fine. Now we will calculate the actual scale height because everything is known now. So H is equal to R star T divided by M bar into G. Everything is known. R star is what is the value of R star? Is 8.314 joules per Kelvin per mole. Remember, this is the universal gas constant. It's not the dry air gas constant or others. Next is T. Given that it is an isothermal atmosphere with 300 Kelvin, means throughout the atmosphere the temperature remains same. M bar is, we have calculated based on the composition, 28.89 grams per mole. And finally, D is the acceleration due to gravity, that is 9.81 meter per second square. Now, just put these values in the expressions and you will get the results. So it is 8.314. Let us write everything. The joules per Kelvin mole. This is your unit. Okay. Into temperature 300 Kelvin divided by mass, which we have calculated, mean molecular mass or molar mass, not molecular mass, molar mass, grams per mole. And what is 9.81 into meter per second. So you can see here, let me change the color to so this is the Kelvin cancels. This mole and this mole also cancel. Okay, other things keep it as it is, and we will see. Okay, so you get, let us put this 8.314 into 300 divided by, okay, grams is not the SI unit, kg is the SI unit. So you have to convert it. So 28.89 into 10 to the power minus 3 kg, and you have 9.81 also you can write meter per second square. And what about here? Joules can be written as what? Kg meter square per second square. And what else? Yes, that's all. So this kg will cancel. 1 meter and second square will cancel. So finally you will get H in meters, which is true, it is perfect. And now if you just calculate all these things, it will come out to be uh, about, okay, so 10 to the power minus 3 can put it in the numerator. So it becomes 8314 into 300 divided by 28.89 into 9.81. You can keep, you can make 9.81 as 10 and try to solve. So finally, the expression will come out to be about 8803 meters or roughly 8.8 kilometers. So that is the scale height. Now, what is the meaning of that? We have calculated the scale height, but what is the meaning of that? Meaning of that is that if your initial pressure is, means at the surface, the pressure is P naught, in that particular atmosphere, it will require to go 8.8 kilometers height where your pressure becomes the surface pressure divided by the exponential of 1, that is E. So P is equal to, P will become P naught by at this 8.8 kilometers. This is what the keel height means. Okay, so roughly about this comes the solution. So let's see. It comes out to be 8810 meters in their case. Okay, let's go to the fourth question then. The fourth question is that in the absence of the sun, how much time will it take for the F region to disappear completely if we only consider the radiative recombination of the electron? We have discussed in the last sessions, as well as it is there in the notes of the main lectures or the video lectures, that radiative recombination as compared to other recombination like the dissociative recombination is a much slower process because it has a very slow recombination rate. And we have calculated that the time it requires when the sun is completely gone, that is at the night time, the time it requires to recombine is much larger because the recombination rate is slow. So it is about 10 to the power 6 seconds. And one of the reactions which I have already told here, this this one. This is the radiative recombination which takes about 10 to the power 6 seconds. Okay, so let me just write. This is the fourth one. That is uh, radiative recombination takes about 10 to the power 6 seconds. Okay, which is a slow process. Okay, let's go to the fifth one then. Sporadic E layer contents. So we have discussed when we were talking about the E layer, we have mentioned in the last session that there is a layer where all the metal ions are present, and all these metal ions which are there in the options are there in the sporadic E layer, whether it is sodium ion, magnesium, or iron. Okay, so all of the above is the correct answer. Sixth is, what is the ratio of the scale heights of oxygen atom? Remember, this is oxygen atom and nitrogen molecule. So let's do this. This is so fifth one is also done. The fifth one, I just write it here. Sporadic P layer consists of metal ions such as your sodium ion, magnesium ion, and ATPs. Okay, so the sixth one is that they have asked to calculate the ratio of the scale height between the age of oxygen to that of the age of nitrogen. I think the opposite they have asked. Yeah, oxygen to that of the nitrogen. Fine, fine. Yes, so age of oxygen to age of. So again, we will use the same expression and assuming that the temperature is constant throughout the atmosphere. So in one case, throughout the atmosphere, temperature is constant, and we will assume that only the oxygen atoms are present. In the second case, we will assume constant temperature and same temperature in case of whatever we have taken in case of oxygen. But now the molecule species, the only molecular species throughout the atmosphere is nitrogen. That's the thing. Okay, so R star, which is universal gas constant, temperature is constant. Only thing which will change is the mass of oxygen into G divided by R star. Same universal gas constant is a universal gas constant. Temperature remains the same. We will assume this mass of nitrogen and G. So all these quantities like your R star T G, R star T G cancel. So finally, the expression becomes only the ratio of the mass of nitrogen divided by the mass of oxygen. Very important. Again, I am repeating that these are the molar masses. Molar masses of nitrogen and oxygen. Sorry, this is molecular. It's not molecular oxygen, it's atomic oxygen. Okay, so the molar mass of nitrogen is how much? We have seen already. It is 28 grams per mole. And the molar mass of oxygen atom, remember, earlier we have taken oxygen molecule. So this is 16 grams per mole. Okay, so just it is the tail height of oxygen atom to that of nitrogen molecule is nothing but mass of molar mass of nitrogen to that of molar mass of oxygen, which comes out to be 28 grams per mole and 16 grams per mole. So this cancels 28 by 16. If you do, it comes out to be about 1.75. This is the answer. And if you get the question, it's 1.75 is the correct option. Next, it is just the definition. What is the transition height is related to what? So transition height is related to what? So we have seen that transition height is an equilibrium height between the two processes, the production, the, the, the first production, and the second is, so it is the equilibrium height of the electron or ion density loss due to N2, that is our beta of H, whatever we have calculated in the earlier expressions, and the production due to the oxygen. So this is the correct option. So it's the equilibrium height. Okay. Finally, which of the following ions have negative scale height? So there are many like O plus, H plus, NO plus, and O2 plus. We have seen in most cases like oxygen, ion, NO plus, or O2 plus, scale height tends to decrease. We have seen for atoms, we have seen for N2 and all those things. But only thing is that for H plus and the helium ion, for these two species, the scale height increases with height. So if you just write the expressions, 8, if you write the expression, so H plus has negative scale height. Why? Question is why? Scale height. Because your H plus is actually proportional to the exponential of H divided by 2 scale height of oxygen. H is the any particular height. So you can see that it is exponentially growing. So it's not, so it's like this. It's not that the concentration is decreasing. This is for in general cases. Okay. Where scale height, yes, scale height is positive. Things should decrease, whether it is pressure or concentration, whatever. But here, in case of hydrogen, or so H plus and helium plus ions, they generally tend to have negative scale height. Okay, so this is how we can say that the scale height is negative for hydrogen as well as helium, but the options are not given for helium. So if it is there, you will have to. Okay, now we will continue our discussion for the week 10 contents, that is this week's content. And yeah, let's see. So this completes our assignment question discussion. It's done. So we will start with the week 10 content. It consists of too many theories, less of mathematics today. Okay. So couple of important points to start with, which is known, very well known. That is, sun is, of course, the main source of energy, but main source of energy for what? For different different processes, like the atmospheric processes or the dynamic processes. Okay, so the dynamics and processes happening in the Earth's atmosphere or in atmosphere. Now, by atmosphere, I mean the entire atmosphere. Whether it is ionosphere, we have seen that solar radiation plays an important role in production of ions and electrons. Okay, so during the daytime, solar winds they generally interacts with the magnetic field. Today also we will discuss some. Okay, it interacts with the magnetic field and try to have different roles and form a magnetosphere layer that we will discuss today. Okay. So not only that, it plays an important role in the lower part of the atmosphere where weather and climate disturbances take place, but it also has an important role in the upper atmosphere as well, which we are discussing right now. Couple of weeks. Okay, so this is very important that this atmosphere, both upper and low. The lower atmosphere leads to different weather phenomena or climate phenomena, and upper atmosphere is ionosphere related phenomena. Okay, so this is one of the important things. Fine. So now let's just go to a couple of important things. So this is we will start with our expression of this the solar constant. Okay, so let's okay. So let us discuss about a term called the solar constant. So how much radiation of the sun is coming into the earth and playing an important role. So we will ask a question that how much amount of solar energy or solar energy that is important uh, is received by the earth per unit area. This is what we call as the solar constant. So how will we calculate this? Okay, simple thing is that if you remember the sun, its surface temperature is roughly about 6,000 Kelvin, right? So based on the 6,000 Kelvin, you can calculate the energy. Okay, so energy per unit area per unit time can be given as assuming sun is a perfectly black body, the perfect black body. Okay, so we assume this perfect black body. Then using Stephen Boltzmann law, so you can write this as sigma t to the power 4, and sigma is, you know, that it is 5.67 into 10 to the power minus 3. units you just right. So this is Stephen Boltzmann constant. Okay, I have written the epsilon is equal to 1 because it's a perfectly black body. Okay, so sigma to the power 4. So if you calculate all these things, the energy which is I will say emitted by the sun based on its temperature is per unit area per unit time is 3.86 into 10 to the power 26 watts. Okay, so now what we will do is that so this is the total amount of energy which is being released. Okay, now Earth to Sun distance is called as one astronomical unit. Astronomical unit. And what is this one astronomical unit means? It's about 1.5 into 10 to the power 11 meters. Remember, 1.5 into 10 to the power 11 meters. Now, if you have sun here and it is radiating in all direction based on the Stephen Boltzmann law, and there is a earth here, okay, which is at a distance of let's say r, which is equal to one astronomical unit, then per unit area. So if you now cover this entire area, which will be 4 pi into this r square, the surface area of this with radius as the distance between the sun and the earth. That is the amount of solar radiation, which is or the solar energy, which is received per unit area of the earth. So the solar constant here is actually the energy which is released by the sun, which is 3.86 into 10 to the power 6 divided by 4 pi into 1.5 into 10 to the power 11 whole square. So now if you calculate this, it will come out to be about 1.715 into 10 to the power 4 divided by 45, which comes out to be 1364 watts per meter square. This is the value of the solar radiation or the solar energy per unit area received at the top of the atmosphere. Remember, this thing is always at the top of the atmosphere, top of Earth's atmosphere. Okay, solar energy received at the top of the. Okay, so this is very important when we are talking about the sun's energy is playing an important role. We must know that how much amount of energy of the sun is actually received per unit area at the upper atmosphere of the earth. Okay, so this is called the solar constant. This is a constant. This is about 1364. Varies with a long period of time. Means about some years, large number of years, 100 years, 1000 years of. On that scale, this solar constant changes very little. It does not change much. It changes very little. Okay. So this is one of the important things. Second important thing is that the spectrum of the solar radiation. So you can see that sun's temperature, as I have already told, that sun's temperature is surface temperature, 6000 Kelvin. And we know that if you have to draw this kind of a graph, that the spectral irradiance is plotted. How will you plot this? You have to understand that at which wavelength it is peaking. So for that, you need the Wien's displacement law, which is about 2898, I think micrometer Kelvin. Okay, so based on that, you can T is this. So lambda max generally comes at the visible So it's about 0.55 micrometer. You can so here, if you just look at these regions, this is in nanometers. Remember, the wavelength here is nanometer. We are calculating in micrometers. So if there is a difference, micrometer is 10 to the power minus 6. Okay, so micrometer is 10 to the power minus 6. Just this is 10 to the power minus 9 meters. So there is a difference. So this dash to dash line is 400 and 700 nanometers. This is called the visible wavelength range. Okay, so visible wavelength range is from your violet to your red. These colors are visible to us, visible to our eyes. That's why those wavelengths, corresponding wavelengths, are called as the visible range. Before that, just before that, you have ultraviolet range. Okay, and you can see there are some molecules written here. These are the molecules which absorb this radiation. So ozone has a tendency to absorb the ultraviolet radiation. So ozones are generally formed and stays at the stratosphere, just above the troposphere where all the weather phenomena takes place. Just above that, temperature increases with height. Why the temperature increases in the stratosphere is because of this ozone. This ozone generally tends to absorb the high energetic UV radiation. So more you go with lesser wavelength, more the energy will be more. Why? Because if you remember, the energy is goes as h nu, right? So hc by lambda, inversely proportional to the lambda. So more less the lambda, more will be the energy. So UV radiation have higher energy. Similarly, as you go beyond visible comes the infrared. So this area is completely the infrared radiation. And the most important part is that Earth. So you know that any body, any object which has some temperature will emit radiation. So how much the Earth emits radiation? So Earth's temperature is roughly about 288 Kelvin. This is for the Earth. Okay. So we have seen that the maximum peak wavelength comes in the visible spectrum. For the Earth, what happens? Because of 288 Kelvin, the lambda max comes out to be about 10 micrometers, which is in the infrared radiation. So Earth emits in the infrared radiation. So remember this. Surface of the Earth, based on its temperature, it emits radiation which whose wavelengths are in the infrared range. But Sun, which has a very strong temperature at the surface, it emits mostly in the visible. The maximum wavelength is in the visible. And you can see that in the infrared part, there are many molecules like the water vapor. This H2 is not water, but this is water vapor molecule. Okay? This is water vapor. So water vapor molecules are there, carbon dioxides are there, oxygen has some peak wavelengths or there are some wavelengths which it tends to absorb. So this is the spectrum of the solar radiation. So different bands are there, different wavelength bands are there, which are being absorbed by different molecules, gases which are present in the atmosphere. Okay, and this plays an important role, particularly in deriving, say, brightness temperatures from the satellites. So satellite calculations are mostly based on these things. Okay, so this is a couple of things which I wanted to share. Next is the internal structure of the sun, not the earth, but the sun. So as you can see that first thing is that yeah, so first thing is that this is the core region. Okay, so this is the core region of the sun, and it has a huge amount of temperature. So in millions, the temperature is in millions degree Kelvin. But as you go towards the surface, which is the say chromosphere, that is near the surface, the temperature drops down to 6,000 Kelvin. But 6,000 Kelvin is also very strong. Okay. So in between, there are two main major zones. One is the radiative zone, another is the convective zone. Radiative zone just above the core. So in the core region, generally you see your nuclear fusion processes taking place. That is, is combining, H is converting into the helium. Okay, this process is constantly taking place, and huge amount of energy is released. This is what is happening in the sun, right? Now, this zone, which is called the radiative zone, okay. So, in the radiative zone, what happens is that matter is still present, okay. So, radiative zone, in the radiative zone, you find that matters are present. So, if matters are present, then how can radiation takes place? Radiation does not require any medium. So if matters are present, the problem is that these matters are nothing but ions, charged ions. Okay. So when you have large amount of charged ions, then what happens is that it does not absorb. Okay, does not absorb energy easily. Okay, so radiative zone, the radiation through radiation, the heats are transferred. So heat is transferred, heat or energy, whatever you want to say, are transferred through radiation. Okay. And finally comes the convective zone. Okay. This, the convective zone. Convective zone, we know that convection, what is the process of convection? Okay. So from higher temperature, this is at a higher temperature, this is at a lower temperature. You can see that there are motions like this. And this is very beautifully seen as granules. There are some granules at the surface of the sun. These granules represent the convection process. Okay, so these are the couple of things. We will come to it later. Okay, and we will see that. Let me see whether, yeah, there are some structures which we will come later on, and we'll write down all the things. Okay, so this is one of the parts. Next is, so before going to the air glow or aurora part, let me just see whether the Earth's magnetic field and all these things are, whether it is mentioned or not. Okay, so yeah, I think this is fine. Okay, let's talk about the Earth's magnetic field. This is the, I have written it magnetosphere, so we can say here as the Earth's magnetic. Okay, see the solar wind, which is being shown here as an arrow. Okay, so sun is constantly throwing some charged particle or plasma, you can say, towards the Earth's surface. So we will note down all these things. Okay, I'm just telling you the processes. So okay, let me just go and write and then come back here. Okay, so we go. here. So let me write here Earth's magnetic field. This is very important. And after that, we will see different processes that will be based. Okay. So first thing is that the Earth's magnetic field, so or geomagnetic field you can say. So Earth's magnetic field is strongly affected by solar winds. Now, what is this solar wind? This solar wind is a stream of electrically charged particles, such as electrons are there, then you have protons, okay, helium nuclei also, alpha particles, okay. So it consists of many things. So it can be called as plasma with low particle density. Okay. Plasma with low particle density. And what is this particle density? Almost approximately about 7 ions per centimeter cube. This is the approximate value of what I call as a low particle density. Okay. Now this solar wind is constantly coming towards the Earth or other planets, but we are considering now the Earth's magnetic field. So we are talking that the solar winds are coming towards the Earth. Now this solar wind, what will it do? It will interact with the magnetic field of the Earth. Remember this Earth's magnetic field. This Earth's magnetic field is particularly because of the dynamics of the Earth. For example, the mantle region, okay, or I would say the outer core region, there are some fluids having charged particles. When it moves, it forms current, and from there is a dipolar magnetic field. Okay, so magnetic field is due to the Earth, not because of the Earth's atmosphere. Now, solar wind coming from the sun interacts with the magnetic field of the Earth. Okay, Earth, and this forms a layer called magnetosphere. Okay, this form a layer called the magnetosphere. So if I go now to this, you can see this entire layer, this entire layer, this is the magnetosphere. Okay, see this from here, all which are except for this, whatever I have shown as the red. So magnetosphere, you can see that this is mentioned here, entire region from here to here. So let me, yeah, this is actually the magnetosphere. Here the interaction is maximum. But before that, there are some, there is also some layer. You can see that magnetosheath is being uh, said there. So what is that? We will see now slowly. Next, what happens is that the solar wind, with respect to Earth or relative to Earth, has a velocity of about 450 kilometers per second, which is supersonic in nature. Okay, so what it does is that on the day side, means the part of the Earth which is facing the sun. Okay, so on the day side, these supersonic solar winds collide with the upper atmosphere. Okay, so this gives you a region of bow shock. These shock waves generally uh, are produced when you have a supersonic aircraft. When it is moving in speed greater than the speed of the sound, find that there is a shock region which is created. Similar thing here comes is the bow shock region. Okay, now comes a region of magnetoshift. This is nothing but a region of turbulent motion just beyond the bow shock region, where the moving charged particle of the solar wind. So here, this is the what I call as this is the magnetoshift. See, this is the bow shock wave which is created, and just beyond that, there is the magnetoshift region. And particles tends to travel. The solar particles tends to travel through this magnetoshift region and gets to this magnetopause and enters the magnetosphere. Okay, so this is the concept. Now, the solar particles consist of ions, charged particles. So these moving charged particles, this moving charged particle of solar wind produces localized current, and this current further produces what we call as IMF, that is interplanetary magnetic field. So there is a geomagnetic field, which is Earth's own magnetic field based on the core dynamics, outer core dynamics, and there is with the interaction of the solar winds, which produces moving charge particles produces some current, localized current, and that further produces a interplanetary magnetic field, IMF. Okay, so this IMF compresses the day side geomagnetic field. Geomagnetic field is the Earth's magnetic field, and weakens or elongates on the other side. This is called the magnetotail or magnetic tail. You can say. Okay. So how it looks like? So if you go to this, you can clearly see. See, this is compressed. This is the compressed region, and this is the elongated region. Look at this. This is the elongated region. Okay. So it is the interplanetary magnetic field which interacts with now the geomagnetic field. So at the side facing the sun, it compresses the geomagnetic field. On the other side, it elongates it. Okay. So this is a couple of things. And what else we can say is that, yeah, with just one point, the charged particles which finally penetrate the magnetoshield are then trapped by the geomagnetic field line, means the Earth's own magnetic field line. Okay. and form the Van Allen radiation method. Okay, so this is an important thing. So now the inner belt consists of generally protons, and outer belt has electrons. Okay, and the charged particle goes in helical motion. Okay, so this is what you have. Okay, so this is what I call as the Van Allen radiation. Okay, so these are the things. Okay, so this completes that the Earth's magnetic field, the expressions of the Earth's magnetic field. So, so refer to the PPT. I will share it. Okay, so this are a couple of things. Okay, the next thing which we will do is the air glow. Air glow, and we will see how it is different from the aurora. Okay, so see this. Okay, so what is an air glow? Let me see. Yeah, okay. So air glow is the faint luminescence found in upper layer of the atmosphere, upper atmosphere. But why they are found? Due to excitation and de-excitation of atoms and molecules by interacting with solar radiation. This is the general definition of the air glow. Remember, this air glow emission occurs in the visible spectrum. Okay, there are few processes which results into this kind of a air glow, or we see these visible wavelengths, because if you are seeing some light, that means some wavelengths are coming, right? So there are two processes. One is fluorescence. Okay, fluorescence, which is some atom which is being hit by a photon, it becomes a star, it goes to the excited state. Okay, and this A star, when come to the ground state, releases a photon. This photon is responsible for the color which we see. So this is from the excited state to the ground state. All right. This is called the fluorescence. Second is chemiluminescence. Almost similar process, but there are some differences. In case of chemiluminescence, you have A plus B is A star plus B. So it goes again to the excited state, but this A star comes like this. The only difference between the fluorescence and chemiluminescence is that it hits by a photon and goes into the excited state. But in chemiluminescence, there is another atom which is coming and hitting, it's colliding with another atom A and making the A go to the excited state. And when it comes back to the ground state, it releases the photon. So this is the same. Only difference is this. Okay, so these are the two processes. So chemiluminescence occurs when there are collisions between atoms and molecules. Okay, but this is only hit by a photon. Okay, so this is important thing. Yeah, so less concentration of atoms and molecules and large amount of extreme ultraviolet photons interacts and the electrons goes to excited state, and when it falls back to ground state, it can be electron, it can be the atom as well. Ground state, the photon is released. So this is the main fundamental thing. Having lambda in the visible spectrum. And that's why you see colors over the sky and all. Same process happens in the aurora, but it is somewhat different. Okay. So the basic differences, let us note it down. Differences between aurora and air glow. These are a couple of differences which I will note down. So one is that air glow can be seen globally. Okay, air glow can be seen globally, but aurora is local to the polar regions. Number two is that air glow is due to interaction of solar radiation with atmospheric constituents. But what is aurora? Aurora, on the other hand, is interaction of high energetic, of course, the solar wind particles with the atmospheric constituent. But remember, atmospheric constituents is found, but in the presence of geomagnetic field. This is very important. So one is happening due to the solar radiation, particularly due to the photons or any other atoms which are colliding. That creates an air glow. But aurora is the interaction of the solar wind particles and the atmospheric constituents, but in the presence of the magnetic field lines. Okay, so this is another difference. Third is that intensity of air glow is generally lower, which is about few hundred Rayleigh. Rayleigh is the unit of intensity, whereas intensity of aurora is high as compared to the air glow. It is about few thousands Rayleigh. Okay, and the fourth, the luminosity of luminosity means the brightness of air glow is uniform, whereas that for aurora is structured. Okay, and so hydrogen, helium, nitrogen, N plus, O plus, OH. These are generally important constituents for the formation of the air globe, but particularly this oxygen and OH has much more contribution for formation of aurora. Okay, so that's a clear thing. Okay, so generally air glow can be air glow emissions can be different. For example, air glow emissions. Let us briefly discuss about them. So there are day glow emission, okay, night glow, and third is the twilight. Okay. So we will discuss about the air glow emissions. So how it happens in a very short way. You can go to the main lecture notes and try to see how it is generally done. Okay. So those things we will see, and then we will see the cause of aurora somewhat, and we'll discuss about the differential rotation of the sun and the granular structure, and again come back to the magnetic field, and will so that is the thing. I think it can this meeting may end. We can rejoin with the same link. Okay. So let us try with now the day glow emission. Okay. Okay, so let's start here. So for the day glow emission, you have O from the 1s state to when O. So these are the spectral state from S to D. It releases 557.7 nanometers. So this is the green line. As you can see, the wavelength is the green line. So these are day glow. Okay. So now you have, suppose these are the couple of spectral states, okay, with different energy, of course. Electron volt, this is 1.96 electron volt, and this is 0 electrons. Okay, so you have 0, 1, 2, these are different states. Okay, so from here to here, so this is your 1s state, this is 1d state. Here to here, the photon which is released is 557.7 nanometers. Similarly, there is another which is the red line emission, which goes to 630 nanometers, which is red. Okay, so these are the oxygen spectra. Okay, now fine. So the first thing is that sources of this O1s thing. Okay, so you have number one is the photo dissociation of oxygen by solar UV photons. So O2 plus H nu, that is the photon, which is less than 133.25 nanometer, which you can see that it is in the ultraviolet region. So O plus, it forms the O1 is this oxygen. The second one of the sources is the three body recombination. So what happens is that here, so these are some reactions you can just you have to see this. So 3p state oxygen, it collides with one any other molecule. This is to conserve momentum and energy. O2 plus M. This O2 plus again combines with 3p oxygen to give you O2 plus this O1s state. Okay, and now these are the productions. Now, how the loss is happening? So O1s is combining with O2 to give you O3p plus O2. So this is the loss. Okay, so one is the production rate. So production rate is given by concentration of oxygen times you have summation for all lambda Iz of lambda comma alpha. Lambda is the wavelength and alpha is the length. Okay, so this times the q lambda. This q lambda is the yield of the reaction, quantum yield. Okay, and this Iz is the intensity. Okay, and this actually is multiplied by sigma AB. Now, what is this sigma AB? Is nothing but the photo absorption cross section. Okay, so this is how the production rate is. Okay, and the volume rate of emission. is the V, which is equal to production times loss. So this is the production times this is loss. Loss is also called as quenching. Okay. So this is thing. Another second is that we have talked about the green line emission. Now let us talk about a red line emission. Okay. This is the red line emission. So how it happens is that O1D, we have seen that from 1D state, when it is jumping to the last state of the P. So this is from O3P plus H nu at 630 nanometers. So this is the photon which is released and it is in red color. Perfect. So now you have O3P plus H nu, the photon energy gives you O1D plus again an H nu, and this O2 plus H nu gives you O1B plus O3. So these are the production processes as you can see. Just like O1 is production, O1D production, and there are loss processes as well. So O1D plus N2 gives you O3P plus N2. So you can see that O1D is lost. Similarly, another process is there, O1D plus O2 gives you O3P plus. These are the loss processes. Okay, again, the volume rate of emission will be production times loss. So in general, this is how it happens. So this is your height and this is your intensity. So this is how, so 250 meters. So peak happens. Okay, so this is the emission rate, the volume emission rate. All right, so this is the, yeah, so these are the things. Okay, and okay, just this completes our air globe. The only thing now is that we have talked about this Earth's magnetic field. Okay, so how Earth's magnetic field is produced, that is not mentioned yet. So suppose this is your Earth. Okay, generally there is a dipole structure like this. So if this is your geographic north and south, this is the south pole of the magnet, this is the north pole of the magnet. This is how this magnetic field lines tends to move. So we'll go like this, remember, because it goes inside the magnet, it goes south to north, and outside the magnet, it goes north to south. Okay, and this magnetic axis and geographic axis has, so geographic and magnetic axis have 11 point, some 11 degrees inclination. So this is important. Okay, nothing else is there here to worry about. Next is we will talk about the sun's magnetic field. Okay, so this is sun magnetic field. Okay, so we will talk about the sun's magnetic field, about the sunspots, and a very important diagram which I have missed in case of your uh, what you call as the internal structure of the Earth that I have missed. I will talk about the granular structure also, and yeah, finally the auroral oval and couple of other things, ring currents, and different types of the magnetism, the interplanetary magnetic field. That we will talk because that will help in solving the assignment questions. Okay, so just a minute. Okay, so sun's magnetic field. So you have in the sun's magnetic field, the first important thing is that the pole reversal in case of sun happens every 11 years. So there is an 11-year cycle. So you can find that sunspot, then coronal mass ejection, then you have plasma. Okay, these are more or maximum during the solar maximum. Okay, so it's an 11-year cycle, as you can understand. This is how it works. So this about 11 years. So from 0 to again coming to 0 is about 11 years. Okay, so now this is the thing. Now within the sun, there are some spots. Okay, and these spots, the corresponding pair of sunspots, can be seen at opposite hemispheres. So these are called the sunspots. So what are these sunspots? These are having temperatures much less than the surface temperature. Surface temperature means the photosphere temperature. Okay. So one is that the center of sunspots is called umbra, which is 4500 Kelvin, and second is edge called the penumbra, which is having 5500. So both of these temperatures are less than 5800 Kelvin, which is the for the photosphere. That is the sun's cycle. Okay, so generally these are black in color, and these are the source of. You can see that the magnetic field lines generally originates from one of the sunspot at one hemisphere and goes into the other. Okay, so that we will see. And these solar activities and all these things happens due to the differential rotation of sun. Sun does not rotate as a rigid body. Okay, so it does not rotate as a rigid body. Okay, so if you have this as the sun and this is the equator, so poles generally move slowly, equator moves faster. So this is the fastest, I would say, which is about 25 days, let's say, and the slowest one is say about 35 days. Okay, so equator rotates faster than the poles. Okay, So this is one of the important parts. You may find question in assignment with this. Okay. And as we were discussing that the solar plasma is trapped in the magnetic field line of the earth. Or okay, magnetic field lines. Here we are talking about the sun. That is the sun. Okay. And this results into corona. Next is solar flares, and number three is the sunspots. Okay, so how it happens? So sunspots, you can see that as I have told you. So sunspots appear in pairs. Okay, so from one sunspot to another, you can see that the magnetic field line tends to go. So these are the pair of sunspots. So you can see that strong magnetic field locks the gas of photosphere and it inhibits hotter gas below to rise at sunspot. Just remember that there are two pairs of sunspots. Two pairs, not two pairs. There can be many, but there is a one pair of sunspots from where the magnetic field lines generally gets trapped. Okay, so these are a couple of things. And yes, in the internal structure of the Earth, this is how the helium and the hydrogen ions tends to or atoms tends to grow. So initially, the hydrogen atoms near the core is being consumed, is fused to form helium, but after that, it grows. So this is 1H1, and for helium, starts well because at the core it is very large, but slowly drops down. This is 4He2. So this is 0, that is core, okay, and this is the 1, let's say, R by R. Okay, so this is important. So this region, the near core, 1H1 fused to form helium, and as we go, you can see that the hydrogen concentration increases, but helium decreases. So that is an important thing. And another thing is that the granular structure of the sun. Okay, so granular structure of the sun. So these are actually the small convective structure. So now, suppose you have This is the sun, this is the equator, and you have these are the sunspots. So this is how, okay. So they appear in pairs, you can see. Okay. So it's in the north, this is the leading. Here, these are the leading sunspots. And what else? So in case of the sunspots, the magnetic field line or magnetic field are stronger. This has, as we have discussed, low temperature. Okay. And these field lines come out of sunspots. With this also we have seen, we have discussed. What else? That's all. Okay. Another important thing is the minimum sunspot activity that happened some centuries before is called the Maunder minimum. Okay. And there is a term called prominences, which is nothing but associated with coronal mass ejections and solar flare. Corona is what? Is hot ionized plasma moving away from the sun. Okay. And what else? Okay, we have also seen that the solar wind is supersonic in nature and it accelerates. This acceleration, so we will study this in next 2 weeks. Okay, this acceleration and what? Yeah. Okay. In case of, so you have this and suppose this is the day side. This is how the charged particles which are trapped in the magnetic field lines, they generally go in a helical fashion. Okay. So Q into P cross B plus QE Lorentz force. So trapped charged particle gets drifted by the field, means the magnetic field. Okay. And they follow helical path. Okay. And these forms, these motion of charged particles create ring currents. Okay, so it is one of the things. And what else? Yeah, that's all. So different types of interplanetary magnetic field. We will discuss this and we will stop for today. These are enough, I think. For okay. Okay. Now, different types of interactions. This is the last part. The magnetic field. Interaction of magnetic field and charge particle. Okay. So I would say the nature of interaction. Let us first write that. So it depends. Characteristics of the body. First one is that it depends on the distance from the sun because the solar winds or the solar charged particles, right? So it depends on the distance from the sun. Number two is the size of the body. Number three depends whether atmosphere is there or not. And finally, whether there is magnetic field is there or not. So it depends on the presence of, or presence, or I would say the absence of intrinsic magnetic field. For example, Earth has its intrinsic magnetic field, okay, but Moon does not have. Okay, so these are the couple of things, the dependencies or the nature of the interactions. Now there are four types. Types can be classified as number one is Moon type. So in the Moon type, what is happening is that no atmosphere or magnetic field. Both are not present. No intrinsic magnetic fields are present and no atmosphere is present. For example, the Moon, because it's a Moon type. Number two is that the solar winds influence the surface because there is no magnetic field and atmosphere, so it directly influences the surface of the planet or stars, whatever, or the satellites, whatever. So examples in these moon types comes the asteroids, Jupiter, the largest planet, Jupiter, Saturn. Oh, I'm sorry, no, it is Jupiter. Wrong. So it is asteroids, other moons of other planets. Okay, this is the second. Second type is Earth type. Okay, this is the Earth type. Magnetic field exists. magnetized. Okay. Solar winds can't penetrate. That's why magnetosphere is created. The magnetic field, right? And it forms cavity, which is called the magnetosphere. Plasma flow of Mercury and Earth and outer planets are dominated by rotation. But plasma flow of the Mercury and Earth are dominated by the electric field. And here the examples are Jupiter, Saturn, Uranus. Of course, Earth is there, so I'm not writing that. Okay. Third type is the Venus type. Okay. So this is also unmagnetized body, but with atmosphere or ionosphere. Okay. But it rotates slowly. This is a very important point. Here the ionosphere exists. So it's good electrical conductor, but weak or no magnetic field. So internal field absent. Okay. So examples of these are your Mars type. Okay. And the fourth one is comet type. So comet type is the, I am not writing, it's a combination of the moon type and Venus type, 1 and 3. Okay. So these are a couple of things. Yeah. So that's all. I think this is fine for today. So what we have discussed so far, let me just slowly go through because we have covered too many things. But since it has no mathematical part right now, so only the theoretical part, so I made some points and discussed it. So let's move from the assignment questions to the week 10 contents. We have talked about a couple of things. For example, the solar radiation, how it affects the earth. So not only the solar radiation, but the solar winds, the charged particles, the ionized particles which are coming to the earth, how it is influencing. The first thing which we have done is that we have seen that the how much radiation from the sun is being received at the upper surface of the atmosphere. That we have seen here as the solar constant. We have derived we calculated the solar constant. Then we have looked at the solar spectrum. We saw that because the temperature of the surface or the photosphere of the Earth, or chromosphere, photosphere, whatever you wanted to say, that has 6000 Kelvin, which is a huge temperature, and as a result, the lambda max, according to the Wien's displacement law, lies at visible spectrum. There are other spectra and different gas molecules absorbs different range of the solar spectrum. Then comes the internal structure of the Earth, where you have core, where fusion reaction, nuclear fusion reaction takes place, releases huge amount of energy. Hydrogen is consumed, helium is released. But as you go farther away, helium keeps on decreasing, hydrogen keeps on increasing because it's a lighter weight. Okay, so in between the core and after the core comes the radiation zone. Ions are present, cannot absorb much of the radiation, so radiation keeps on releasing the heat towards the surface. Now, at the surface or near the surface, you have a convective zone where convection processes are dominated. And yeah, so finally, you get the surface, which is called the photosphere, having temperature 6000 Kelvin. After that, we have discussed about the magnetosphere, Earth's magnetic field. Earth has its own magnetic field because of the outer core, which is in fluid and it is rotating. The outer core having charged particles creates current and magnetic field. And these are the dipolar magnetic field. Okay, we have this is the typical structure of the magnetic field. Day side it is compressed, night side it is elongated. As you can see here, called the magnetosphere. Solar winds are nothing but coming from the sun, some ionized gases, charged particles. When it comes into the and interacts with the Earth's magnetic field, it creates a bow shock region because the solar winds are supersonic in nature. And some of the charged particles gets into the magnetosphere and they get trapped in the magnetic field lines and they rotates in a helical fashion and forms your ring current. Okay. So these are the couple of things which we have discussed. And we have discussed actually many things of the geomagnetic field. So these are the dipolar structure which I have mentioned. Okay. And interplanetary magnetic field is being created because of the solar charged particles creates local current that produces an interplanetary magnetic field which interacts with the geomagnetic field. Then we came to air glow and we have discussed about fluorescence, chemiluminescence. The basic difference is one is hit by the photon, another is not hit by the photon but collided by the atoms or molecules. Okay. Next is aurora and air glow differences and different day glow and night glow processes, emissions, and how we can write the reactions. We have seen that sun's magnetic field generally arises from the sunspots, which are regions of lower temperature and black in color. So from there, the magnetic field lines originates, and it occurs always in pairs. So magnetic field goes into the other. Okay, and differential rotation of the sun produces those sunspots, coronal ejections, and all those things. The equator moves faster as compared to that of the poles. It's not a rigid body rotation. Okay, and then sun's surface you can see some granular structure which represents the convective up branch, upward branch, or downward branch. Okay, and yeah, so ring current also I have mentioned, and different types of magnetic field and charged particle interactions. So nature of interaction depends on couple of features like the distance from the sun, depends on the size of the object, like Earth's size or moon size, whatever. Depends on whether the atmosphere is present or not, and the internal magnetic field is present or not. So there are four types, categorized into four types. One is the moon type, where no atmosphere and magnetic fields are present. There are some examples. Earth type, where magnetic field is present, atmosphere is also present. So they behave in a different manner. Venus type, where you don't have magnetic field, but you have the atmosphere, ionosphere, and the reactions happen in different ways. And comet type is a combination of the moon type and your Venus type. So I think with this, we can end today's session. And if you have any questions, we can discuss in the next class. Okay. Thank you.